Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture, if you recall, we derived the different stress components under a pure bending situation, right, and there we have seen that all the stress components are 0 except sigma x, and that sigma x is equal to minus my by I z z, right. So, that we have derived, and that was only for pure bending situation, right, when your bending moment is constant throughout the beam, and there, and based on that we derived the expression for the deformation, that is your strain, okay. And there also we have seen that how we can get all the, how we can get all the strain components, normal strain components rather, all the shear strain components are 0. Now, today we will be talking about stresses in symmetrical elastic beams transmitting both shear force and bending moment. So, in the previous lecture whatever we had derived, so that was based on pure bending situation. So, there was no shear force acting on the beam, but here in this particular topic actually we will be discussing if you have both shear force and bending moment, then what will happen. Now, we will make the assumption, okay, that the bending stress distribution, whatever distribution you have seen, that is minimum at the neutral axis and maximum at the top surface or the top fiber as well as the bottom fiber, right. The extreme fibers will be experiencing more, maximum bending stress, right. But at this moment we will make the assumption that the bending stress distribution is valid even when the bending moment varies, okay, along the beam. That means, if the bending moment varies, that means shear force is present, because you know dmb dx is nothing but v. So, earlier case, in case of pure bending, when the bending moment was constant, so dmb dx was simply 0, right. So, that is why your shear force was 0, but now we are considering that bending moment is varying, okay, across the beam. So, therefore, dm by dx is not 0, that means it is a non-zero parameter. So, therefore, your shear force is not a 0 component, okay. So, that is present, very much present in the beam. So, if you consider, this is a part of the beam, okay. So, long slender beam. So, consider a length of delta x of a beam, okay. So, consider a length of delta x of a beam which is subjected to both bending and shear force. So, bending is shown here, okay, and shear force also, okay, right. Now, no, we are not considering any external transverse load, okay, no external transverse load on the element, so that the V is independent of x, that means V is not varying with x, okay. So, therefore, we are getting constant V on both the faces. So, this is your positive x face and this is your negative x face, okay. So, on both the faces your V is same. So, V is not varying at all. So, we are because there is there is no external transverse load. If you do not have the change in force, okay, so transverse load, then your shear force will not be changing, okay, it will be constant throughout the beam. Now, if you look at, but your bending moment is varying, because if shear force has to be present, then bending moment has to vary. So, bending moment is varying. So, on this face, on this side your bending moment is mb, and but on this side your bending moment is mb plus delta mb. So, a variation in bending moment with x is represented by this increment delta mb, fine, okay. Now, consider the equilibrium of the segment of beam, okay. So, if you come back to this, and based on our previous discussion already we know that, and we are making the assumption that whatever we have derived in the last lecture, that holds good even if you have the shear force present in the beam. So, therefore, your distribution of the bending stress will be like that. So, maximum at the top fiber and the bottom fiber, Whether it is compression or tension, that is different issue, but it will be maximum as per the magnitude wise, it will be maximum at the top and the bottom fiber, whereas it will be simply 0 at the neutral surface. Okay, fine. So, consider the equilibrium of the segment of beam. Okay, so this is one segment we are considering. So, in this figure. Okay, so we are considering one segment. So, this is one segment where if you consider this is a kind of braid, we are cutting a slice, okay, along the x plane, along the x axis. Okay, okay. So, consider the equilibrium of the segment of beam which is obtained, okay, by isolating the part of the beam element above the plane defined by y is equal to y 1. Okay. So, this plane, so this is nothing but y plane. Okay. This plane is defined by a distance y is equal to y 1 from the neutral surface. Okay. We are taking one slice, and now we are considering the equilibrium condition of this particular segment. Now, one thing is very clear, because this is a kind of a continuous, say, continuum body. Okay. Now, each and if you make n number of slices, okay, so every slice will be getting bonded with the adjacent slice, and you will be having some interface shear force or interface, say, force which will be bonding these two say fibers together. Am I right? So, if you consider a top part of the beam, and immediately after that there is one adjacent part. So, these two parts will be getting bonded at the interface. Okay. So, therefore, you should expect, okay, you should expect one force which will be getting developed at this y plane along x direction, yes or no, right, to balance the forces acting on the x plane. On the x plane you are having the axial force. Now, you are getting the variation in the axial force because your bending moment is varying. Am I right? If your bending moment is varying, any particular section, if your bending moment is varying, as you know from our previous discussion, that your sigma x will be varying because bending moment is varying. If sigma x is varying, then who will try to balance this variation? The variation will be balanced by the force which will be getting developed on this y plane. So, that is nothing but delta f y x, okay, on y plane along x direction. So, therefore, if I consider the equilibrium condition, okay, so that means summation of f x, summation of all the forces in x direction is equal to, say, 0. Okay. So, therefore, I can write simply A1, integration over the area A1 sigma x dA, okay, at x plus delta x distance, that means on positive x plane, say, minus delta f y x minus integration over the area A1 sigma x dA at x equal to 0. So, that means what I am doing? So, the first term, that is integration over the area, because this, if you consider, this is the area A1 that is given here. Okay. On this area, if you consider small area, say delta A or dA, whatever, okay, on this area your sigma x into delta A is the force acting on this small area, and if you integrate over the whole area A1, then you will be getting the force on that particular area A1. Okay. So, that is acting on this face, say. So, the first term is acting on this face, which is x plus delta x distance apart. Okay. Now, similarly, the last term, if you consider, that is the integration over the same area, because this area will be remaining same, and sigma x into dA on this plane, that is at x distance apart, and delta f y x, because what we are considering that all, I mean this on this face we are considering say tensile force, I mean outward, I mean towards the positive x axis. Similarly, to balance it you will be having the force in this direction. So, that is why it is negative, and delta f y x is also acting opposite to x axis as shown by this arrow. So, therefore, delta f y x is also coming as negative. So, these are the forces, okay, which are acting along x direction. Okay. So, now from this I can simply write delta f y x equal to minus integration over the area A1, okay. Instead of sigma x, now we can write, as we know, what is the bending moment at that particular section at x plus delta x distance. If you consider one section that we are considering, so what will be the bending moment there? So, delta mb, okay, y by I z z. So, that is the value of sigma x at x plus delta x into dA, okay, plus integration over the area A1, and what is the bending moment is acting at x distance apart, I mean the on the section which is x distance apart, that is mb simply, okay, mb y by I z z into dA. Okay. So, now further I can write delta f y x is equal to minus delta mb by I z z a1 y dA. Let us say equation 1. Okay. Now, dividing both sides by say delta x and taking the limit, what we will get? So, what we are doing? We are dividing both sides of equation 1, okay, by delta x and taking the limit. Okay. So, that is nothing but d f y x dx is equal to limit del x tends to 0 delta f y x delta x is equal to dmb dx into 1 by I z z integration over the area A1 y dA. Agreed? So, just we are taking the limit and we are dividing both the sides of equation 1 by delta x and taking the limit. So, that will be coming like that. Okay. So, now if you look at this, so I can again write that d f y x dx equal to, what is this? If you recall from our previous discussion, that is nothing but minus of V, right, the shear force. So, I can simply write V by I z z, okay, into integration over the area A1 y dA. Okay. So, this is my equation say 2, since your dmb dx equal to minus V, that we know from our previous discussion. Okay. So, now from this basically if we put this dfyx as qyx, dfyx dx as qyx, okay, and q, capital Q is equal to integration y dA. If we put like that, then I can simply write q yx equal to vq by izz. There is a very important relation we have established. So, that is equation say 3. Now, where your qyx, what is your qyx? If you look at qyx, that is given by dfyx dx, right. So, that is nothing but total longitudinal shear force transmitted across the plane defined by y is equal to y1 per unit length along the beam and is called shear flow. Very important term. Okay. So, what is qyx? That is the total longitudinal shear force, okay, transmitted across the plane defined by y is equal to y1. So, at y is equal to y1, you are defining one y plane. Okay. So, you are defining one y plane. On that plane, your shear force is acting, that is delta f yx is nothing but the shear force is acting on that plane. Fine. So, basically qyx is that shear force per unit length along the beam. Along the beam, your x is there. So, dfyx dx is nothing but the shear force acting on that particular y plane, okay, per unit length of the beam along x direction, okay, and is called shear flow. That is very important. So, that is the shear flow on that particular plane per unit length, okay, per unit length. If you move along the beam, that is the shear force acting, okay, and your capital Q is nothing but the first moment of the shaded area, okay, A1, that is shown in the figure about the neutral surface. Agreed? So, integration y dA is nothing but your q, and that is nothing but your first moment of this shaded area, okay, A1. Agreed? Okay. So, this equation is giving you, so what you are getting from this? This q is basically defined by the plane on which you are interested to find out the shear flow, okay. Izz is nothing but the cross sectional property, as you know. So, if you know the shear force, then you will be able to find out how much shear flow, okay, how much shear flow per unit length of the beam is acting on the beam along, I mean on the beam along your x direction, that means on the y plane, okay. So, now if you try to find out the, so therefore, this is nothing but your shear force, I mean shear flow is nothing but the shear force per unit length of the beam. So, you can find out, so your qyx is basically is the resultant of a shear stress tau yx on the y plane along x direction, okay. So, tau yx distributed across the width B, okay, of the beam. What does it mean? So, this shear flow is acting on this plane. So, this is the plane on which shear flow is acting, as you see, this is the plane, okay, y plane. Now, if you this tau yx is basically giving you, that is per unit length, okay, whatever shear force is acting. So, therefore, it is a resultant of a shear stress tau yx distributed across the width B. So, this is the width B. So, this, if you consider this whole part, basically this whole part is giving you the qx, qyx. So, qyx divided by B is nothing but the shear stress acting on that particular plane, okay, fine. So, if we can say that, then immediately I can write down tau yx equal to qyx by B is nothing but equal to Vq by Bizz. Very important equation. So, if you are having the varying bending moment across the beam, that means if shear force is present, then basically your shear stress will be also getting developed, and that tau yx, that is the shear stress, is nothing but equal to Vq by Bizz. So, and we know from our earlier discussion that tau yx is nothing but tau xy, which is again Vq Bizz. Okay. So, now you can say, you can see the variation, or I mean distribution of tau yx on this plane. So, this is your tau yx, this is your tau xy, right, both are same and both are equal to Vq by Bizz. Now, if you look at this expression, okay, so what we can write, basically the shear stress has a constant value along the negative y plane, okay, and on the x planes it varies from this constant value at the bottom to 0 at the top. Okay. So, what does it mean? The shear stress has a constant value along the negative y plane. So, on this plane, so this is the negative y plane, okay, this is your negative y plane. On that plane your shear stress value is constant, because there actually your q is constant, V of course is constant on that particular section, and then Bizz, all those things are constant. So, you are getting the constant shear force on that particular plane. But when you are talking about the shear stress on the x planes, that means when you are talking about the shear stress on these planes, then basically it varies from this constant value, okay. So, the constant value will be at the bottom, okay. So, this is the constant value, because here at this is the junction of y plane and the x plane. So, along y plane you are having constant tau yx, and along this say point, along this line, okay, on the x plane you will be having the constant value. but as you move to the top your constant value will be going to 0, because your q is becoming 0. Q, what is q? Q is the first moment of this area. So, as you move from this point, to the top surface, your q is getting reduced, right, is not it? Your q is getting reduced, that is the first moment of that shaded area is getting reduced. So, ultimately when you will be going to the top surface, okay, your q will be becoming simply 0. So, once q is becoming 0, then tau xy will be becoming 0. So, this is the variation of tau xy from the. So, what does it mean then? That means in case of bending stress, that is sigma x when you calculated, that was simply 0 at the neutral surface and it was maximum at the extreme fibers, right, extreme surfaces. But here in case of your shear stress, it is just reverse, it will be maximum at the neutral surface, because at the neutral surface if you consider, you will be getting maximum magnitude of q, but as you move towards the extreme surface or the extreme say fibers, your shear stress will be becoming simply 0. Okay. At the top and bottom your shear stress will be becoming 0 and in between it will be varying and it will be taking the maximum value at the neutral surface. Okay. So, now next we will be talking about, now I will stop here today. So, in the next class we will be talking about the stress distribution in the. So far we have considered the section in such a way that it is symmetrical with respect to your xy plane, but now we will be considering the rectangular cross section, and then will be, which is more common. I mean generally you see this kind of rectangular beam, right, the cross section is rectangular or square whatever. So, that kind of say cross section if you have, then how your shear stress will be getting, how much will be your shear stress on that particular rectangular cross section, that we are going to find out in the next class. So, I will stop here today. Thank you very much.